Got that going. So today we are going to be finishing up chapter 6. Now, high-level language, what has chapter 6 been about so far? Angle congruence. That's what it's been about. Chapter 4 was about segment congruence. Chapter 6 is all about angle congruence. And so the postulates, the new postulates that we introduced, were all about angles and how angles are congruent. So remind you of postulate group 5 so far. What was our first postulate? High-level language, it meant if I gave you some angle and I gave you some ray on a line, but some ray, how many angles can I create with this ray congruent to this angle?
One on either side.
2. One and only one on this side with this ray, and one and only one on this side with this ray. That's essentially what it says. So it says, given a non-straight angle, remember it has to be non-straight, given a non-straight angle A, and a ray R prime on L prime from some point A prime. So given the ray and some angle A over here, there exists a unique ray S prime on either side of our line L prime. Sorry, this is L prime. Such that angle A is congruent to angle A prime. So there's one and only one ray on this side that makes this angle congruent to this angle, and there's one and only one ray on this side that makes this angle congruent to this angle. Good. What was our second one in high-level language, our second postulate?
That was your says that angle congruence is an equivalence relation.
It says angle congruence is an equivalence relation. It says pick any angle you want, it's for sure congruent to itself. It says if angle A is congruent to angle B, then perfect. And if angle A is congruent to angle B and angle B is congruent to angle C, then
Angle A is congruent to angle C.
perfect. And this property is called the reflexive property. Everything's congruent to itself. This one is called symmetric. And then this one was called transitive. Fantastic. And then finally, our third one. What's our mnemonic for remembering our third postulate? What do we tell our...
Equals add to equals is equals.
Equals add to equals or equals and...
Equals subtracted from equals or equals.
Equals subtracted from equals or equals. Perfect. That's exactly what this says in terms of angles. And so, the first two are going to say equals subtracted from equals or equals, because there's two ways I can subtract off of this angle. If I've got angle A composed of angle B and angle C here, I can either subtract off the C piece or subtract off the B piece, right? So this one says, if angle A, that's the whole thing, is congruent to A prime, and B is congruent to B prime, then C is congruent to C prime. So I take the A, subtract off the B's, and the result being C are congruent. Similarly, if A is congruent to A prime and C is congruent to C prime, then
B is
congruent to B prime. And then finally, equals add to equals or equals is this one. And it says that if B is congruent to B prime and C is congruent to C prime, then
A is congruent to A prime.
A is congruent to A prime. Perfect. Now our last postulate, which was the one that enabled us to start proving triangles are actually congruent to each other, a huge part of geometry, was our side angle side postulate, not our side angle side theorem, two different things. What did our side angle side postulate tell us? It says if I have two triangles, here's triangle ABC and A prime, B prime, C prime. Can you see the primes okay?
Yeah.
So I've got these two triangles. If I know that they have a side congruent to each other, an angle congruent to each other, and a side congruent to each other, so you get a side, angle, side all congruent to each other, in that order, the angle has to be between the two sides. It couldn't be this side, this angle, and this side. So if you get a side, angle, side all congruent to each other, then you know that the two remaining corresponding angles are congruent. So if I know this, then I know angle B is congruent to angle B prime, and I know angle C is congruent to angle C prime. Those were all the postulates we introduced last week. And in fact, this is it for our postulates in this class, with the exception of one more, I think. Our parallel postulate, I think, is the only one we're missing now. So we've almost completed all our postulates for geometry. All right, so any questions about the postulates so far? Just remind you of all those. And then we'll quickly recap all the theorems we proved last time, and then some of the more important definitions. So recapping our theorems from last time. We proved that if two angles are congruent, then so are their supplementary angles. So what does that picture look like? If I know that this angle is congruent to this angle, then I know that their supplements are also congruent to each other. You remember that one?
Yeah.
Oh, missing part of one, I forgot it again. Another part of one is all straight angles are congruent to each other. And that's what we used here. We said this line is congruent to this line. If this piece is congruent to this piece, then that piece has to be congruent to that piece. And that's how we proved it. Our second theorem was vertical angles are congruent to each other. So vertical angles are when I have two lines intersecting, right? And I want to say that this angle is congruent to this angle. How do I prove that this angle is congruent to this angle? Well, this angle right here is congruent to itself. This is a supplement of this, and this is a supplement of this. And so, supplementary angles, if an angle is congruent with another angle, their supplements are congruent to each other. Since this is congruent to itself, its supplement is congruent to its supplement. That was our big idea for that one. And then we proved that an isosceles triangle's base angles are congruent. What's an isosceles triangle?
A triangle with two congruent sides.
Two congruent sides. So I draw some triangle here. Triangle ABC. And I know that this side is congruent to this side. I'm trying to prove that its base angles are congruent. I'm trying to prove that angle B was congruent to angle C. And what was our big idea there? Our big idea was to relabel this triangle two different ways. We could talk about this as triangle BAC and triangle CAB. And those two triangles are congruent by side, angle, side. Or they're not congruent, but they satisfy side, angle, side. And so their corresponding angles are congruent. So this angle must be congruent to that angle. And that was a big idea for that proof. Just a double labeling. So that was proving that the base angles of an isosceles triangle are congruent. And then we finally got to our side angle side theorem, our first congruence theorem for triangles, actually proving two triangles are congruent. So your side angle side theorem states that two triangles are congruent. Your side angle side postulate didn't quite give you that the two triangles are congruent. The postulate only gave you all three angles and two of the sides. It didn't give you this remaining side is congruent to this remaining side. And that was the crux of this proof. Is to prove that if we have this picture here, then this side is in fact congruent to that side. Right? And how did we do that? We found a point on this triangle that had the same distance as this point on this triangle. We called that point, I can't remember, something like E. And then we proved that E was also on this angle. So since E was on this angle and on this angle, it has to be where those two rays intersect, and they intersect at B prime. And so that point is B prime, and so those sides are in fact the same length. That was our big idea for that picture. And then we went through angle side angle. We did a similar thing that we did in this proof, where we found a point on the side and showed that was on the intersection of two rays, and so we got a side angle side. And then using side angle side, we proved angle side angle. But so now, here are our two congruence theorems so far for saying that two triangles are congruent. If you know that they have a side angle and side corresponding to each other, the two triangles are congruent. And now you know if they have an angle side angle corresponding to each other, then the two triangles are congruent. That's what we've proven so far. We have one more congruency theorem that we're going to prove in this chapter, and that is the side-side-side congruency theorem, which is if two triangles have all their sides congruent to each other, then the two triangles are congruent. So we'll be proving that today. Our last theorem that we proved last time was a bit easier one. It was another double labeling. We showed that if two angles in a triangle are congruent, so are the two sides opposite the angles. So if I draw a triangle, so that this angle is congruent to this angle, then this side is congruent to this side. That's what we were trying to prove. And how did we prove that? We double labeled this triangle. So we'll put the A on the top. Call this triangle ABC. I said that triangle ABC is congruent to triangle ACB by angle side angle, and therefore their corresponding sides are congruent. And that was the idea behind that proof. So that's quickly running through everything that we proved last week. I want to remind you of two important definitions from last week. First off, what was the definition of a right angle? What did it mean for an angle to be a right angle?
An angle that's congruent to its supplement.
Perfect. So if I have a right angle, I know that it is congruent to its supplement. So if this is a right angle, it's congruent to its supplement. And our other definition was what it meant for two triangles to be congruent. If I say triangle ABC is congruent to triangle DEF, what exactly does that mean? That means segment AB is congruent to segment DE, segment BC is congruent to segment EF, and segment AC is congruent to segment DF. Order matters. When I write these letters in a particular order, I am communicating very specific information. And I'm also saying angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. And that is exactly what we're saying when we say that triangle ABC is congruent to triangle DEF. If I were to draw two triangles here, try and read into my picture. I know pictures, we usually say pictures lie, but I want you to tell me the right way to order this. So let's call this ABC, and be trying to draw a congruent triangle down here now. And I'll call this the point H, I'll call this the point R, and I'll call this the point S. What triangle is congruent to what triangle?
Triangle ABC is congruent to RHS.
So ABC is congruent to, and you have to keep the same order. What angle were we saying A was congruent to?
R.
R. So if A comes first here, when we write this triangle, we better put R first. What angle were we saying B was congruent to?
H.
H. And what angle were we saying C was congruent to?
S.
S. And furthermore, we were saying segment AB is congruent to RH. We were saying AB is congruent to RH. And we were saying BC is congruent to what?
HS.
HS. So BC up here better be congruent to HS. And finally, we were saying AC is congruent to what?
RS.
RS. And so that was stating this. So order very much matters. It would have been very wrong for me to say triangle ABC is congruent to triangle HRS. That is not true. That is false. This is not congruent to that, because angle A is not congruent to angle H. So order matters. That's the important point with that definition. Good? Okay. So with that, let's jump into our first theorem, the side congruency theorem. How is this theorem going to work? Maybe I'll scribble down here for a second. So I've got some triangle here, and I've got another triangle here. And I know that this side is congruent to this side. I know that this side is congruent to this side. And I know that this side is congruent to this side. I'm trying to prove that these two triangles are congruent to each other. You with me? Here's what I'm going to do. I'm going to come down here. I'm going to construct down here a triangle that I know is congruent to this one. So this angle is some measure here. Whatever that angle measure is here, I'm going to use it to put a ray down here so that this is congruent to that. How do I know I can do that?
From your postulate group 5-1.
First one right here. You give me some angle. I pick this side of this line, and there's one and only one ray I can find that makes this angle the same big as that angle. I'm going to mark off a point here so that this is the same long as that. And that's going to give me this triangle down here. You with me? Now I know that this triangle is congruent to this triangle by side, angle, side. Side, angle, side. Which means that this side is the same big as that side. And now over on these two triangles, I'm going to drop down this vertical line. And that's going to give me this isosceles triangle right here. And this isosceles triangle right here. And what do I know about the base angles of isosceles triangles? They're congruent. So I then know that this angle is the same big as this angle. And I know that this angle is the same big as this angle. And equals added to equals are
Equals.
so this whole angle is the same big as this whole angle. So now I got this triangle is congruent to this triangle by side, angle, side. So I know this, I constructed this bottom one to be congruent to this, and it turns out this top one is congruent to the bottom one I constructed. Therefore, the two triangles are congruent to each other. That's the big picture thinking there. So I start with my two triangles. I'm going to construct this bottom one to be congruent to this one, and I show that this bottom one is also congruent to that one. That's the scribble thinking. Here's trying to give a bigger, better picture of it. So we're going to go over that thinking again. I just wanted to give it to you all in one go and then slowly absorb it. So restart. So here we go. Let triangle ABC and triangle A prime, B prime, C prime, such that AB is congruent to A prime, B prime, BC is congruent to B prime, C prime, and AC is congruent to A prime, C prime. So all the triangles have all their sides congruent to each other. So triangle ABC, that's this one right here. And triangle A prime, B prime, C prime, that's this one right here. With me so far? So we got that triangle and that triangle with all their sides congruent to each other. Okay, step 2. I'm going to construct ray A prime, B prime down here on the opposite side of A prime, C prime as B prime. So my ray is for sure coming down here. And I'm going to construct it such that the angle from my resulting ray, angle C prime, A prime, D prime, is congruent to angle A. So I've made this ray down here so that this angle is congruent to that angle. Now I'm going to pick E prime on my ray such that A prime E prime is the same big as A prime B prime. In other words, I'm intentionally constructing a triangle down here that I know will be congruent to this thing. So I intentionally made sure this side was the same big as that side. We already got that for free. I made this angle as big as that angle. And now I'm going to make this side as big as that side. And now this triangle, A prime, C prime, E prime, is going to be congruent to this triangle, ACB. Let me say that better. C prime, A prime, E prime is going to be congruent to CAB by side angle side. So that's exactly what I say here. So then triangle E prime, A prime, C prime is congruent to BAC by side angle side. Make sure that we have corresponding, make sure our order is right here. What point does E prime correspond to up here? B. So I did E prime, then A prime. What does A prime correspond to? A. And then C prime corresponds to?
C.
C. And that was by side, angle, side. Side, angle, side. So I know that this triangle down here is congruent to this triangle. Right? Okay. What we're trying to now show is that this triangle is also congruent to this triangle. That's what remains to be shown. I know that this is congruent to this. Now, since this is congruent to this, we finally get that E prime C prime is congruent to what? E prime C prime is congruent to what? BC. Let's see, where do we write our triangle congruence? I know that we're right here. Sorry. I know that triangle E prime, A prime, C prime is congruent to BAC, and so I know that E prime, C prime is congruent to BC. I wrote CB instead of BC, but same thing.
You also wrote C.
Oh, I wrote C prime, E prime, so I intentionally did that. Wait, C prime is the latter one. C is the latter one. Okay, I did it right. So I showed that the segment from here to here are congruent. From the last letter to the first letter. As long as I'm doing the same orders, we are using this correctly. But I already know that CB is congruent to C prime, B prime. So I showed that this side is congruent to this side, but this side is congruent to this side. So this side is congruent to this side, using transitivity. Good? Okay. I'm trying to argue now that this triangle is congruent to this triangle. Here are my two congruency theorems. I either need to find a side angle side or an angle side angle. So I'm trying to show that this triangle is congruent to this triangle. What are we going to use? Side angle side or angle side angle?
Side angle side.
We want to use side angle side because we know that three sides are the same. It's easier to find one angle than two angles. So I need to find some angle on this top triangle and show it the same big as an angle on this triangle. And that's when we drop down this blue line, and we notice that that creates two isosceles triangles. The isosceles triangle on this side of the blue line, and the isosceles triangle on this side of the blue line. Right? So, observe that triangle, E prime, A prime, B prime, E prime, A prime, B prime, and triangle, E prime, C prime, B prime, are isosceles. Right? And so what do we know about the base angles of isosceles triangles? They're congruent. And so, these two base angles are congruent, E prime, B prime, A prime. So E prime, B prime, A prime is this base angle. We'll use two lines here. Is congruent to B prime, E prime, A prime, B prime, E prime, A prime, which is this base angle. And E prime, B prime, C prime is congruent to B prime, E prime, C prime. So this one is congruent to this one.
And you know that because the supplements of an angle are.
No, I know that because the base angles of an isosceles triangle are congruent. An isosceles triangle's base angles are congruent. Theorem 6.3. Make sense? Okay. And now, that angle is congruent to that angle is congruent to that angle, so this whole angle is congruent to this whole angle. How do I know that?
Equal that equals
By postulate.
Yeah, postulate 3, the third one right here. The postulate 5.3. So by postulate 5.3, so then I know that this whole angle, A prime B prime C prime, is congruent to this whole angle, A prime E prime C prime, by postulate 5.3. Okay, so now I have a side, angle, side, side, angle, side. And so I know that my bottom triangle is congruent to my top triangle. So then my bottom triangle, my top triangle, A prime B prime C prime, is congruent to my bottom triangle, A prime E prime C prime, by side, angle, side. Right? I know that side is congruent to that side, that angle is congruent to that angle, and that side is congruent to that side. So by side, angle, side, I know my top triangle is congruent to my bottom triangle. And then, since I already know that this triangle is congruent to this triangle, then using the transitive property for all our congruences, I now know that this triangle is congruent to that triangle. So, since this triangle, A prime, E prime, C prime, is already congruent to triangle ABC, that's how we constructed it, then triangle A prime, B prime, C prime is also congruent to triangle ABC. This is congruent to this, is congruent to this, and so this is congruent to this. You follow that proof? That's a tough one. There's a lot going on. Hopefully going over the picture twice helps. Good? Good enough? Enough that you can start absorbing it? You can go back and watch the lecture 3 more times. All right. Let's move on now to our next theorem. So we had a definition for a right angle, but how do we know that there is such a thing as a right angle in our geometry? So we said, what was a right angle? An angle congruent to the supplement. Do we ever get an angle that's congruent to the supplement? What if I came up with a name for an angle? I'm going to call it an angle Bob. And what's our angle Bob? It's an angle that's over 570 degrees, assuming it's an angle that's greater than a straight angle. There we go. But a straight angle is the biggest angle you can have. So it doesn't exist. I can make up a name for some angle. That doesn't mean it magically exists.
Right.
So name things however you want. It doesn't mean that they're real. You might have your imaginary friend Bob. Doesn't mean he exists. So we're going to prove right angles, in fact, exist. Good? All right. What is going to be our picture idea for our right angle here? There's 3 different pictures. I'm only going to walk through. Well, I've only got one of them drawn up here, but let's scribble out our 3 possible cases. Here's what we're going to do. We're trying to prove that a right angle, in fact, exists. So I'm going to start with some line. Do I just call it L? Yeah. So I'm going to start out with some line L, and I'm going to pick 2 random points on L. Pick some point on L, call it O, and then pick another point on L, call it B. Good so far? How do I know a line contains 2 points? All the way back to our first postulates.
Yeah.
I also know that there's a point not on the line. How do I know that? All the way back to our first postulate. So, and I know that there's some point out there in the universe, call it point A. Good so far?
Yeah.
Now, what I'm going to do is I'm going to look at this angle right here. And I'm going to construct a ray on the other side congruent to that angle.
Okay.
So I'm going to get some ray down here. So that this angle is congruent to that angle. I'm then going to find the point A prime on this ray. So that was an awful one. It's because my picture is somewhat lying. Let me just draw my point first. I'm going to find some point on my ray, A prime, such that this distance is the same big as that distance.
Okay.
With me? Then I'm going to look at, since I know that A and A prime are on opposite sides of this line, there has to be a point on the line between them. So I may call the line on the point on the line between them D. And then I'm going to argue that this angle is congruent to this angle. How do I argue that this angle is congruent to that angle?
By proving that the triangles are congruent.
And how do I know that these two triangles now are congruent?
Side angle side.
Side angle side, because this side is congruent to itself, this angle is congruent to this angle, and this side is congruent to this side.
Yeah.
So this triangle is congruent to this triangle, so this angle is congruent to this angle. So it's congruent to its supplement. Therefore, it's a right angle.
How do we know that that is a supplement?
Because D is between A and A prime, so this is collinear. So the two angles produce a straight line.
Okay.
Good question. That's one possible picture. The other possible picture is, how do I know that B was on that side of O? B could have been on that side of O. O and B were just 2 points. So my other picture could have looked like this. I could have had L here, O here, and then this time B's over here.
Does it matter? Why can't you just relabel them?
It almost doesn't matter. We'll see why it almost doesn't matter. Oh, sorry. O and B, yes, we could always relabel. Keep it O and B. That's not what I meant to say. I meant to say my A could have been on the opposite side of O as B when you draw this line through.
Oh, okay.
So my A could have been over here.
Okay.
If my B was over here, just flip the picture and it's all the same. So let me try and say it again. So here's where another version of what our picture could have been. L's here. We could have had O's here, B's here. But this time, A isn't on the same side of O as B. A is instead a point somewhere over here. We go through the same process, construct a ray, so that this angle is congruent to this angle. But now when we drop this line down to get our A prime, our triangle isn't using the angles that we know are congruent. Over here, our triangle was using the angles that we knew are congruent. Over here, it's not using those angles. So we first need to argue that this angle is congruent to this angle. How do I know that?
Because supplements are congruent.
Supplements are congruent to each other. So I know that this is congruent to this. By construction, this was the same big as that, and now by side, angle, side, those two triangles are congruent, and so this angle is congruent to this angle. So it's the same idea, there's just one more step added to say instead of starting with these angles being congruent, we're starting with their supplements being congruent.
And then you can prove that they're congruent by.
And then these two triangles are congruent by side, angle, side.
Yeah.
Right?
Yeah.
Our final picture on how this could have happened is going to look like this, where the point O and A are the same point, or O and D. O is equal to the point D. So our A could have been directly above O. And our B is over here. Here's the last way our picture could have looked. Our A could have been between O and B, our A could have been on the other side of O as B, and then finally our A could have been directly above O. By construction, we make our ray down here so that it is congruent to this angle. So if that's the case, then that angle is congruent to that angle by construction of our ray. So there's our three pictures. Now let's go over the proof with the heart of the proof in just one of the pictures. Okay, so right angles exist. Let O and B be any points on L, and A not on L. So A is just some random point not on L. O and B, two random points on L. A, some random point not on L. Let R be a ray from O, containing some point C. I don't care where C is on the ray, but it's somewhere on the ray. And that's just putting a point C on there for naming purposes so we can talk about our angles. So let R be a ray from O containing some point C, and our ray is on the opposite side of L as A. A is up here, so our ray is on the opposite side of L as A, such that angle DOA is congruent to angle DOC. So we made it so that DOA is congruent to DOC. In other words, we found the ray down here congruent to that angle. That's all we were after. I just put the C on there so I can name this angle somehow. Okay, now I find A prime on this ray such that OA is congruent to OA prime. Right? Which gives me these two triangles now. So I got these two triangles. I know that that angle is congruent to that angle. I chose the ray to make that true. And now I know that this side length is congruent to that side length. I found the A prime on this ray. That makes that true.
And OD is congruent to OD.
So now, this triangle is congruent to this triangle by side angle side. This side is congruent to that side. That angle is congruent to that angle. And that side is congruent to that side. If it helps you, put 2 tick marks on that side. It's congruent to itself. So, let A prime on R such that, we already did that. Oh, no, we didn't. I just said it, but I didn't read it yet. So let A prime on R such that OA is congruent to OA prime. And let D on L such that D is between A and A prime. How do I know that there's a D on L between A and A prime? Because they're on opposite sides of the line. I chose R to be the ray on the opposite side of L as A. So I know the points on R are on the opposite side of L as A. And what does it mean for 2 points to be on opposite sides of the line?
There's a point on the line between them.
There's a point on the line between them. So I know that there's D, some point on the line between A and A prime. And now we have 3 cases. We could have had D is on the same side of O as B. We could have had D was on the opposite side of O as B. So D could be on the same side of O as B. D could be on the opposite side. Here's D in this case. D could be on the opposite side of O as B. Or D and O could in fact be the same point. Those are our 3 cases. We've got to handle each of those 3 cases. So let's start out by assuming D is on the same side of O as B. So that's our picture here. D and B are on the same side of line L, are on the same side of O as each other. First case, right? Here's O, here's L, D and B are on the same side of O. Okay, so that's the case we're starting with. So if that's the case, then triangle DOA is going to be congruent to triangle DOA prime by side angle side. And so angle ODA is congruent to angle ODA prime. So this angle is congruent to this angle, and those 2 angles are supplements. And so if an angle is congruent to its supplement, what does that mean? It's right angle. So that gives me that angle ODA is in fact a right angle. Okay, we found it. A right angle if it comes out that case. But it didn't have to come out that case. So our next case now is let's assume D and B are on opposite sides of O. So let's re-scribble this picture really quick for D and B being on opposite sides of O. And draw out the construction one more time. So I've got my line L here. I've got O. I've got B. I've got A. Step 1, what did I do? From O, I found a ray, R, such that, well, we'll make that segment, such that this angle and this angle are congruent. I found the ray R that makes that true. Then I found the A prime here, such that this length is the same exact length, and now we got this triangle, and D is now over here. So this is our picture. Sorry, that's an awful D. Okay, so we're right here. Assume that D is on the opposite side of O as B. Or in other words, O is between D and B. Then what happens? So observe that angle DOA is congruent to angle DOA prime. DOA is congruent to DOA prime. How do I know DOA is congruent to DOA prime? Because their supplements are congruent. This angle is congruent to this angle, so this angle supplement, which is U, is congruent to this angle supplement, which is U. Right? And now I know that these 2 triangles are congruent by side angle side. Side, angle, side, side, angle, side. So in that case, So I said angle DOA is congruent to angle DOA prime, since their supplements are congruent, and so then the 2 triangles are congruent. So then triangle DOA is congruent to triangle DOA prime by side angle side, and so this angle is congruent to this angle, and so it's a right angle. Same thinking as we used in the first proof, or the first part of the proof, right? And now the last picture we have to handle is a case where D and O happen to correspond to each other. So our last possible case we could have drawn is I've got my points here. So I've got L, I've got O is here, I've got B is here. And it could have been the case that the A that we chose, that's not on the line, happened to be directly above O. It could have been that A is right there. What did we do? We look at this angle, and we construct down here an angle, a ray down here, so that this angle is congruent to this angle. Right? Find the point between them, call it D, and so if D is equal to O, then this is already a line. And I constructed so that angle is congruent to that angle. So those two angles are, they're supplements and they're congruent, and so they're right angles. We're proving that right angles exist. So this was the last possible case. So no matter what the case is, we ended up with the right angle. I think we have everyone.
Perfect. Good morning. He's awesome.
Okay, so that's the last case that we're going to handle here. So assume that O is in fact equal to the point D. And so then angle AOB is already congruent to angle A prime OB by construction. And so they're right angles. Those were the three cases. All those make sense?
Yeah.
All right. Now, the big, bad, scary definition of the second half of this chapter. And it's going to be talking about angles being less than or greater than each other. And I know this was already a pain with segments. Going back thinking about segments, what did it mean for one segment to be longer than another segment?
That the point B prime was beyond point B.
Perfect. So if I've got some segment AB, and I've got some segment on a line here, we'll put some line, and I've got some segment on this line, A prime, B prime. If I'm saying that AB is bigger than A prime, B prime, that means that there exists a point B double prime over here, such that this segment is congruent to this segment, and B prime is between A prime and B double prime. So, we'll just write that in words over here. What did it mean for AB to be less than, or to be, we did greater than, right? AB to be greater than A prime, B prime. That meant that AB was congruent to A prime, B double prime, and that we had A prime, B double prime, where B prime was between them. That's what it gave us. Now notice that this does not say the same thing as A prime, B prime is less than AB. What does it mean to say A prime, B prime is less than AB? So now, reset, I've got these two segments, and this time, I want to say that this is less than this.
Means if you find a point on the line that contains AB.
It means up here, there exists a B double prime, such that this is congruent to this, and now our between this relation goes A, B double prime B.
Yeah.
So one's talking about a picture messing with this line, another one's talking about a picture messing with this line. They do not say the same thing, and we had to prove that if this was the case, then this was the case. And it was an ugly proof and we didn't like it. Because we want to instantly go from thinking if AB is greater than A prime, B prime, then obviously A prime, B prime is less than AB. But they say different things. And so we're going to see, with comparing angles, we run to the same thing. Saying angle A is bigger than angle B is not the same thing as saying angle B is less than angle A. We will prove it's the same thing, and that will be the big bad theorem that we have remaining in the class, and then it's pretty easy from there. So, wrap our head around this definition, prove our last hard theorem, and then smooth sailing. All right, you ready?
Yeah.
Jump into this. You got it. Stick with me. Okay, so let angle A and angle B be non-straight angles. We're going to talk about one being greater than the other. We're always going to say that a straight angle is the biggest angle, and nothing is bigger than a straight angle. So let angle A and angle B be non-straight angles, and let B prime be our angle, such that B prime is congruent to angle B. And Let's say it with our picture here before we read it in words, because this picture is going to be a mouthful. So here's angle A. Here's angle B. Which one are we going to do first? Oh, both those are going to be setting up our picture for how we draw B prime. So I'm going to be setting up a B prime here, so it's the same big as B inside of angle A. And there's two ways that this can happen. So here's our B, here's our A. I'm going to construct B prime down here. It's going to share a side with A, and that's going to have another ray that isn't the same as A if the two angles aren't the same big. Right? So if I construct B prime so it's the same big as B, it could be the case if A happened to be bigger, then the ray that we construct is in between, is in angle A's interior. It could also be the case if B happened to be bigger than A, then if I come down on A and I make an angle as big as angle B, then our ray is going to be in A's exterior. Those are going to be the two cases. Here's what it's going to mean to say that angle B is less than angle A. Here's what it's going to mean to say that angle B is greater than angle A. If when you reconstruct the angle, the other side falls in the interior, it's smaller. If when you reconstruct the angle falls in the exterior of A, it's bigger. That's what we're going to say. A lot of words to say this picture because it's kind of technical to say exactly what this is. So here comes the word salad describing this picture. So let angle A and angle B be non-straight angles, and let angle B prime such that B prime is congruent to B. B prime shares a side with A, so B prime and A have one side in common. And where is B prime's other side?
In the interior?
Well, it could be in the interior or it could be like this.
Right.
So it's not necessarily in the interior, but it's on the same side of the shared side as the other side of angle A.
Right.
That's a lot of words for a simple picture, which is what this is going to say. So I've got angle B and I've got angle A. I'm constructing B prime so that B prime is congruent to B. So it could be like this or it could be like this. Constructing B prime so it's congruent to B. And B prime is going to have one side in common with A, and it's going to have its other side on the same side of the shared side as A's other side. Just a word salad setting up this picture. So it's kind of a convoluted picture to set up when you're doing your proofs. Just say let B prime be the angle given to us by, let B prime be the angle congruent to the smaller angle or whatever. Don't try and go through all the words of setting that up exactly right. It's a big word salad, and you'll probably mess it up. It's hard to say. But that's what that's saying, is saying up that picture. Now it's saying in this picture, we have two cases. Either R, the other side of angle B prime, lies in the interior of A, or it lies in the exterior. If it lies in the interior, then B must have been smaller than A. If it lies in the exterior, then B must have been larger than A. So that's what this is saying. If R lies in the interior, lies interior to angle A, then we say angle B was less than angle A. If R lies in the exterior of angle A, then we say angle B is greater than angle A. Good? And then finally, as a third part of this definition, we say if angle A is a straight angle, and angle B is not a straight angle, we always say angle A is bigger than angle B. So you can't get bigger than a straight angle. Now can you think of an angle bigger than 180 degrees?
Yeah.
What's bigger than 180 degrees?
270.
270. So you might be thinking, what are you talking about? Isn't this angle, 270 degrees, bigger than this angle? Right? Isn't this angle bigger than this angle? And the answer is no. This angle's teeny. It's just that little thing right there. And you're saying, no, I meant to measure it this way. I meant the 270 degree angle. We have no notions of degrees yet, no notion of numbers. An angle is 2 rays, and that's all it is. You're not going to put that and say, I want you to think about my 2 rays this way. An angle is just 2 rays from a point. So 2 rays from this point, 2 rays from this point, that's all you get. Which angle's bigger?
Straight angle.
The straight angle. And you don't get to say, well, think about if we went around the circle 18 times and then ended up here. No, there isn't any motion, there isn't any movement. It's just 2 rays. And now which one are we going to say is bigger than the other? and we will get to degrees later. Now I lied to you, I said that's chapter 7, and I don't know why I said that. That's way down the road. It's like chapter 10. So we have a long ways to go before we introduce degrees. So for now, all we can think of an angle is just two rays, and so do we want that to be bigger or that to be bigger? In our geometry, we want that to be bigger, because orientation shouldn't matter. Go ahead.
When we do introduce degrees, can we say that there are angles bigger than straight?
We will have a way of talking about them. And so there will be a difference between the angle and a measure we assign to the angle. And those are two different things. When we say that that angle is 90 degrees, that's technically false. An angle is not degrees. What is an angle? It's two rays. It's a geometric object. It's not some number. We're saying that this degree assignment is a measure that we can assign to that angle. And it works with our rules. And you could have also assigned 270 degrees to that. And that's a measure you could have assigned to that angle and have it work. So those are going to be two separate things. The angle and then the measure of the angle. Very different. An angle, just two rays. That's all it is. Okay. So that is going to be our definition. Good? And the intuition for why straight angles are the biggest makes sense now? If you think all you get is two rays, you don't put any numbers on there, you have to call that bigger than that. Right? Okay. So move this over, but hopefully keep definition 6.5 so that we can reference it. Oh, sorry. So, have that definition. Let's jump into the big one. I'm glad I did this on the whiteboard because I want all the different colors. Okay, how is this one going to work? So what are we proving? We're going to prove that if angle B is less than angle A, then angle A is bigger than angle B. So I'm going to start with, we're proving an if-then statement. What's the first line of an if-then proof? What's the first thing you do? Assume the antecedent. So assume or let angle B be less than angle A, where angle A is composed of rays R and S, and angle B is composed of rays T prime and S prime. So just labeling the rays for the future of the proof. But their names really don't matter so far. So I've got angle B, or angle A is this big one, and angle B is the smaller one. I drew them in black. That's our starting picture. Just the two black rays. Or I guess four. Two here, two here. So I know that angle B is less than angle A. I know that angle B is less than angle A. What does it mean exactly for angle B to be less than angle A? So that's this one right here. What do I know if I know angle B is less than angle A?
That line that's raised by the interior.
Then there exists this ray R in the interior, so that this angle is congruent to that angle. So, since I know that this is smaller than this, I know that there exists this ray up here, ray T, so that blue is congruent to blue. You see that? Now, what am I trying to prove? I'm trying to prove that angle A is bigger than angle B. What does it mean for angle A to be bigger than angle B? That means that when you draw this ray, it's falling out here in the exterior. So when I come and I construct this angle A prime, I need to prove that this R prime is in the exterior of angle B. That is the whole crux of this proof. So I know that this ray, T, is in the interior of A. My whole proof is to prove that this ray, R prime, is in the exterior of angle A. That's everything I'm out to do. You with me? Now, how can I prove that my ray R prime is in the exterior of angle A? In the exterior of angle B? How can I prove that this ray R prime is in the exterior?
Prove that it isn't on D side of T and...
If I can find one point on the ray that's in the exterior, then the whole ray has to be in the exterior. That's going back to one of our older theorems. Either the whole ray lies inside the angle, directly on the angle, or completely in the exterior of the angle. That's how rays have to line. We can't have rays crossing in the interior and the exterior going back and forth. That led to contradictions with lines intersecting lines more than once. Make sense? So I'm going to pick some point here. I'm going to pick a clever point here, C prime, on this ray, and I'm going to prove that C prime is in the exterior. How am I going to do that? I'm going to find this point E prime, and I'm going to prove that E prime lies on this ray, where E prime is between C prime and D prime. Since E prime is on, I'm going to prove that it's on that ray. Since C prime is on the opposite side of E prime as D prime, then C prime has to be in the exterior of the angle. That's a big picture how this is going to work. So, taking it from the top, all we've got is blank. I've got angle A and angle B. I know that angle B is what? Less than angle A. So, let angle B be less than angle A, where A is composed of these two rays and B is composed of these two rays. Sorry, I keep touching my picture and slowly erasing it. Okay, since I know that since I know that B is less than A, I know that there exists this ray T such that it gives me an angle congruent to angle B. So, since angle B is less than angle A, then, I've introduced this symbol to you guys, right? There exists? Okay. So then, there exists ray T in the interior of angle A, such that the angle composed of S and T, call it angle B prime, is congruent to angle B. So I know that there exists this ray, so it gives me blue angle congruent to blue angle. That's what I know so far. Okay. Let R prime be the ray from B on the same side of S prime as T prime, such that the angle it creates, angle A prime, is congruent to angle A. So I'm constructing this ray R prime. The whole crux of our proof now is to show that R prime is in the exterior of angle B. And we're done. That's all we're trying to show, is that this green ray is in the exterior of angle B. So far, the information I know angle blue is congruent to angle blue, and angle green is congruent to angle green. That's my information so far. Good? Now we're going to label some points. Let C on R, D on S, C prime on R prime, and D prime on S prime, such that AC is congruent to BC prime, and AD is congruent to BD prime. In other words, pick a point on this ray, and find the corresponding point on this ray, so that side length is congruent to that side length. And pick a point on this ray, and find the corresponding point on this ray, so that side length is congruent to that side length. You see that? So now that gives me this triangle here. And the triangle CAD is going to be congruent to the triangle C prime B prime D prime by
Side angle side.
side angle side. So now we've constructed those points. Observe that triangle CAD is congruent to C prime B D prime by side angle side. And so that gives me that angle D prime is congruent to angle D. So now I know red angle is congruent to red angle, because the two triangles are congruent. Okay, what are we going to do next? We're going to let E be the point where T intersects CD. So E is a point where T intersects CD, and I already know that E is between C and D. Right? So it's this picture like this. I'm now going to choose E prime on C prime D prime. I'm going to choose E prime on C prime D prime, such that ED prime is the same length as that. Now I've got two problems. First off, I need to prove that E prime isn't clear out here. That's the first thing I need to prove. And the second thing I need to prove is that E prime in fact lies on T prime. Because I do not know, just because I find the E prime here, that makes that congruent to that, I do not magically know that E prime doesn't go beyond C prime.
Right.
So that's the first thing I have to handle. So let E be the point where T intersects CD. That's how we got E up there. And now, let E prime on C prime side of D prime, such that DE is congruent to D prime E prime. So find that, such that this is congruent to that. Now, I know that D prime E prime is congruent to DE. I know that this is congruent to this. And I know that DE is less than DC. How do I know that this length is less than this length?
Equals, subtracted from equals are equal.
Well, yeah, but essentially I know it because I know that E is between C and D. How do I know E is between C and D?
Because
T is on the interior.
Because it lies on T, and T is in the interior of angle A. That was my starting given information. Since I know that this angle was smaller than this angle, its corresponding ray is going to be interior. So, I know that D prime E prime is congruent to DE, but DE is for sure less than DC. And DC is congruent to what?
D prime and C prime.
D prime C prime. And so now I know for sure that DE prime is in fact less than D prime C prime. Which means that E prime has to lie between D prime and C prime. You with me?
Yeah, that makes sense.
Okay, so I've got E is between D prime and C prime. So E is for sure in so I've got that ordering for sure. I know that E prime is for sure between D prime and C prime. Now if I can show that E prime lies on T prime, that means C prime has to be in the exterior of this angle. Because here's D prime and C prime on either side of E prime, is one way you can think about it. And so they have to be on opposite sides of that ray. So what remains to show is that E prime lies on T prime. And then we're done. So now the second thing to observe is that triangle E prime D prime B prime, E prime D prime B prime, no B prime, just B. Triangle E prime D prime B is congruent to what? EDA. B prime is just a measure of that angle.
yeah.
EDA. So I know that this triangle is congruent to this triangle using E prime.
Right.
Which means that this angle and this angle have to be congruent. So that means that the angle we create with EBD prime has to be congruent to the angle we create with EAD. But the angle we create with EAD is the same big as angle B. So that's our argument here. This triangle is congruent to this triangle using E prime there. We're arguing that E prime has to in fact lie on T. That's what this is arguing. So this is a bad picture. The only way to make this picture correct is to put E prime on that ray T. So bad picture, we're arguing E prime has to be on ray T prime. So, observe that triangle E D prime B is congruent to EDA by side, angle, side. And so their corresponding angles, this angle has to be congruent to angle EBD. So, where did I say that? That by side, angle, side, which gives me that angle E prime B D prime is congruent to EAD, but EAD is exactly equal to B prime, that is that angle. So that's not congruent, that's equals. That's two ways of naming the same angle. Angle EAD is angle B prime. That's exactly what it is. And I already know that angle B prime is congruent to angle B. So I get that E prime B D prime is congruent to angle B. How many angles are there on this side of this line congruent to angle B? 1. And so this angle, E prime B prime D prime, and angle B have to be the same angle. Which means E prime has to lie on ray T prime. That's the big argument there. So, that gave me that E prime B D prime is congruent to angle B. So then E has to lie on angle B somewhere because they name the same angle. Or in other words, E has to lie on the ray T prime. And now we've got it. And so we've got E as a point on T prime. So now let's put our picture so it makes sense. So this is what the picture has to look like. E prime has to be right there. And so since E prime is on T prime, and since C prime is on the opposite side of E prime as D prime, where D prime is also on the angle, Then C prime can't be a point between them. It has to be in the exterior. It can't be in the interior. Or in other words, C prime is definitely not on the same side of this ray as this ray, which is what meant to be in the interior. Okay, so since E prime lies on T prime, and since E prime is between D prime and C prime, where D prime was a point on the other ray, that's important. D prime is for sure on this ray. That's where we were. Since E prime lies on T prime, and since E prime is for sure between D prime and C prime, then C prime is in the exterior of angle B. Which gives me, probably should have specified, what does that mean? That gives me that R prime is in the exterior. And now, since R prime is in the exterior, that gives us what? That angle A is bigger than angle B. Because when you construct its corresponding ray, it falls in the exterior. Giant proof for something that's real easy to say and something that's very intuitive. This is one of the proofs that the author put an asterisk next to. He says, which is what he does when he says, you probably don't want to try and prove this in class. Too much for the students to swallow. I have a higher opinion of you than the author does. I know that's a lot. Don't expect you to be able to reproduce the proof, but want you to see the proof. Okay. So now, we're through the hard part, a couple easy stuff, and then we're done for today. And then you get your big Thanksgiving break, where you get to do all your Chapter 6 homework, and don't get a break.
Don't get a break from the break.
Nope, a break is a chance for you to get caught up on your homework from teachers who give you too much homework.
We don't have math. We don't have geometry next week, though.
Yeah, no geometry next week.
Or
Yeah, 2 weeks ago.
English, by the way, you guys.
I believe so.
Because I don't think she assigned.
Bro.
Yeah, no geometry next week, kind of. You're still busy all day Tuesday next week.
Are we?
Yeah, all your Chapter 6 homework.
Yeah.
So you've already got that marked out on your calendar. You're not just going to take a week off and then think, oh shoot, I should have done Chapter 6 homework, because there's a ton of it. This Chapter 6, it's the hardest chapter in the book. We're almost over the hill. So go hard over the holidays, get the homework done, engage with it. Once you get through that, it's just smooth sailing through the rest of the class. If you don't get Chapter 6, you're dead for the rest of the class. Because we are going to use these theorems over and over again. There's a reason that when you took geometry back at Masada, that they just had you memorize side, angle, side, side, angle, because this stuff is ubiquitous in geometry. It never goes away. And after geometry, you'll likely take a course called, what comes after geometry? Trigonometry. What is trigonometry? What's its etymology? The study of triangles. So this never goes away. Whatever helps. All right. So don't give up on Chapter 6. It's the most important chapter in the book. Get Chapter 6, and it's smooth sailing from here on out. Anyways, now some easy theorems. All right. So Theorem 6.9. Given angle A and angle B, then we have to have one of three cases. We have to have angle A is bigger than angle B, angle A is congruent to angle B, or angle A is less than angle B. It has to be one and only one of those three cases. What is the big idea of the proof? So I've got some angle here, and I've got some other angle here. I'll draw them roughly the same size, so that my picture could almost intuitively go either way. Here's angle A, here's angle B. So now if I were to come and construct the angle corresponding to angle A down here, it could come in one of three ways. When I construct the other ray, using this same ray as my starting point, when I construct my second ray, it could either come out here. When I construct my ray, that gives me an angle congruent to that angle. It could go on the exterior. It could have landed right on B. Or the ray could go inside the interior. And those are the only two cases. If the ray goes on the interior, then A was smaller than B. If the ray lands exactly on B, then the angle was the same big as B. And if the ray lands on the exterior, then the angle was bigger than B. And it has to be one of those three cases. The ray can only go one place. So does my other ray go in the interior, does it land right on the angle, or does it go in the exterior? That handles all our cases. And so each case gives us one of these corresponding relations. So I'm essentially going to say that in words. The only case I didn't handle is dealing with straight angles. So now, here's everything. So if both angles are straight angles, so if angle A and angle B are both straight angles, then what do we know?
All straight angles are congruent.
They're congruent to each other. So then we get this one. Remember, I'm arguing no matter what these angles are, we're either going to get A is bigger than B, A is congruent to B, or A is less than B. We're going to get one of those three cases. No matter what A and B are. So let's handle the case where both angle A and angle B are straight angles. In that case, then, they're congruent. Okay, we only got one of those. Now let's handle the case where one of our angles is straight and one of them isn't. If one of my angles are straight and one's not, what do I know?
The one that's
The straight angle's bigger.
the straight one, yeah.
So, let's handle that case. And if only one of them is straight, we'll call angle A. What if angle B was straight and angle A wasn't? Well, relabel them. And call B A and call A B, and now we're back to where we started. So, if only one of them is straight, call angle A, then angle A is bigger than angle B. Because a straight angle is always bigger than a non-straight angle. Okay, handle those cases. Now, let's assume that neither angle A or angle B is straight. So now we can use this definition. Let angle A and angle B be non-straight angles. So now we can just use that definition. So, assume that neither angle A or angle B is straight. And now here's what happens. Let angle B prime such that angle B prime is congruent to angle B and angle B prime shares a side with angle A, and both angle B and angle A have their non-shared side on the same side of their shared side. In other words, set up our picture down here with B prime. So we're either setting up this picture or we're setting up this picture. Or R could have landed exactly on A's other side. Let R be B prime's non-shared side. So we're going to label our ray R. Or scribbling over here since that's off camera. So I've got, here's angle A, here's angle B, and I'm going to construct B prime. We'll do B prime in blue. One of B prime sides shared with angle B, and then its other side is either going to come up, I'll do its three possibilities with the dotted line red. Its other side R, B prime's other side could be like this, R, or it could be like this, R, or it could be like this, R. When we get our corresponding angle B prime. Has to be one of those three cases. So let R be B prime's non-shared side. So B prime is our measure from blue up to red. If R lies in A's interior, if R is down here, so our B prime is this angle, well, that's exactly what it means for A to be bigger. That's what it means for B to be less than A, but we now know that B less than A is the same thing as A greater than B. So that's what it means for B to be less than A, or in other words, A is greater than B. Okay, our next case. So if R lies in A's interior, A is greater than B. If R lies in A's exterior, then A is less than B. If R lies in the exterior. And then finally, if R lies on angle A's other side, then angle A is congruent to angle B. Those are the three cases. That's all there is to it. So the other ray has to land somewhere. Does it land in the interior? Does it land directly on it? Or does it land in the exterior? And that gives you your three cases. Good? Hopefully that one's as straightforward as I think. Okay, Theorem 610, we're not going to prove any of these. They're pretty straightforward proofs. And they're ones that you can already guess the answer to, so you're just going to tell me the answer to all these. But the theorem tells me all these things hold. I didn't finish it, you're going to tell me what holds. So if angle A is congruent to angle B, and angle B is less than angle C, then
Angle A is less than angle C.
angle A is less than angle C. So that's part of the theorem. Next part of the theorem says, if angle A is less than angle B, and angle B is congruent to angle C, then, once again, angle A is less than angle C. Next it tells me, if angle A is congruent to angle B, and angle B is greater than angle C, then,
Angle A is greater than angle C.
perfect, angle A is greater than angle C. Next it tells me, if angle A is less than angle B, and angle B is less than angle C, then,
Angle A
A smaller than B, B smaller than C,
Angle A is less than
A smaller than C. That gives me that angle A is less than angle C. And then next, if angle A is greater than or equal to angle B, and angle B is greater than or equal to angle C, then
Angle A is greater than angle C.
greater than or equal to angle C. Perfect. Angle A is greater than or equal to angle C. And the author approves the first one, and he basically just gives a quick sentence explaining it. He doesn't go through explaining the full picture. It's a very, you can basically see it, right? Type proof.
Yeah.
So, not worth going through. You can read his if you want. Okay, finally, second to last definition here. If an angle is greater than a right angle, if an angle is bigger than a right angle, what do we call it? Obtuse. And if it's less than a right angle, we call it acute. Perfect. That's all that definition is. Next proof is that all right angles are congruent to each other. We know that all straight angles are congruent to each other. We need to prove all right angles are congruent to each other. Now, here's some thinking you might be tempted to use. I've got a right angle here. Let's construct a right angle. Here's a right angle. We'll call it A. If it's a right angle, what do I know about its supplement?
It's also right.
It's right. It's also a right angle, and these are congruent to each other. So I know A prime is congruent to A. Let's pretend that the measure of this angle is x. So these two angles added together is 2x. And 2x is equal to a straight angle, right? 180 degrees. Let's now draw another straight angle, or another right angle. So here's some other right angle, call angle B. It's going to be congruent to B prime. Call the measure of it y. And so once again, I get 2y is equal to 180 degrees. Now if 2x equals 180 degrees and 2y equals 180 degrees, what do I know about x and y?
They're the same.
They're both 90 degrees, or they're both the same. If I know that this is equal to one straight angle, say 1s for one straight angle, and I know that this is equal to one straight angle, then I know 2x equals 2y, or in other words, x equals y, they're the same. And so you're very tempted to use that thinking when you're saying all right angles are congruent to each other. The problem with that thinking is it requires us to measure angles. So this thinking does not work because we do not yet have a concept of measuring angles. So our starting picture is going to be like this. I've got A here is a right angle, so it's congruent to A prime. I've got B here is a right angle, so it's congruent to B prime. How do I know that A is congruent to B? That's what I need to argue. We pick any two right angles, A and B. I now need to prove that those are congruent to each other. Another thing you might get tricked by is A is a right angle, A prime is a right angle. I know they're congruent to each other. Doesn't that show all right angles are congruent to each other? Here's two right angles, and they're congruent to each other.
Shows that it's congruent to its.
Yeah, it just tells me a right angle is congruent to the supplement, which is the definition. The question is this right angle congruent to this right angle? And that's what we need to prove. So I need to show that angle A is congruent to angle B, where I know angle A and angle B are right angles. So setting up our picture here, here's angle A, here's angle A prime. I know red is congruent to red. Angle B is right there, and angle B prime is right there. Forget the red and green down here for a second. Just look at the black and the blue. And I know blue angle is congruent to blue angle. Maybe make sure you can see that blue angle goes all the way through. Right? So I got A is a right angle, so it's congruent to its supplement. I got B is a right angle, so it's congruent to its supplement. I'm trying to argue that angle A is congruent to angle B. That's my thinking here. You with me? Yeah. So set up our picture. Let angle A and angle B be right angles, and let angle A prime and B prime be their supplements. So that's setting up just the black. Ignore the green for a second, and ignore the C's down here. With me? It's just setting up basically this picture. Okay. Now assume by way of contradiction that angle A is not congruent to angle B. Let's assume that angle A is not the same big as angle B. And we're going to show that this is impossible until they have to be the same big. So if angle A is not the same big as angle B, we're going to get a contradiction.
Are you saying angle A is congruent to angle B or is not congruent to angle B?
Thank you. Assume by way of contradiction that angle A is not congruent to angle B. Good. All right. It's always nice when someone's paying attention. So we're going to show that this leads to something impossible, and so angle A has to be congruent to angle B. So if angle A is not congruent to angle B, what do we know?
That it's either greater than.
That it has to be bigger than it or smaller than it. Because it has to be one of these three things. Right?
Yeah.
So, without loss of generality, assume that angle A is smaller than angle B. What do I mean by assume without loss of generality?
The previous statement still.
Without loss of generality means we could relabel these things and it doesn't matter. What if angle B was actually smaller than angle A? Well, then relabel angle A, angle B, and angle B, angle A, and angle A prime, angle B prime, and angle B prime, angle A prime, and now we're back to where we started.
Yeah.
So without loss of generality means we can relabel everything so that this is true no matter what. So I know that angle A is not congruent to angle B. I know that the two angles aren't congruent. We're going to call the smaller angle, angle A, and the bigger angle, angle B. Because one has to be smaller and one has to be bigger if they're not congruent to each other. So let's say that A is smaller than B. Well, what does it mean for angle A to be smaller than angle B? It means that we can construct this ray in the interior so that this angle is congruent to angle A. That's what it means for one angle to be smaller than another angle. What does it mean for one angle to be smaller than another angle? When we construct its corresponding ray to get congruence, it's in the interior. So I'm going to construct angle C here, congruent to angle A, and its ray is going to be in the interior of angle B. With me? And if it's in the interior of angle B, it's in the exterior of angle B prime. Right?
Yeah.
So, here's my angle C. So, let's see. Let angle C in angle B prime, such that angle C is congruent to angle A, and call the side of angle C not shared with angle B R. So here's angle C, and call the side that it doesn't share with angle B R. That ray. With me so far? And now let C prime over here be the supplement of angle C sharing side R. So make sure you use the supplement over here and don't accidentally try and use the supplement down here. So now that's C prime. With me? Okay. Now what do I know? I know A is congruent to C, right? And so what do I know about A prime and C prime?
They're congruent
They're congruent. How do I know that?
because
Supplements of congruent angles are congruent. Since A is congruent to C, then the supplement of A is congruent to the supplement of C. Remember, we're setting up a possible and picture. We're doing a proof by contradiction. We're showing that if angle A is not congruent to angle B, we get an impossible picture. So if your intuition is screaming, that doesn't look right, that's because it's not right. That's the point. We're proving it's not right. Okay, so I know angle A is congruent to angle C. That's how I chose this ray R. R is the ray that makes this congruent to this. And now I know that C prime is congruent to A prime because it's the supplement of congruent angles. Now I know that A is a right angle. What does it mean for A to be a right angle? It's congruent to A prime. So C is congruent to A, is congruent to A prime, is congruent to C prime. So how does C compare with C prime?
They have to be congruent.
They have to be congruent because C is congruent to A is congruent to A prime, and A prime is congruent to C prime. Okay, so say that here and now it works. Let C prime be the supplement of angle C, sharing the same side R. Observe that since angle A is congruent to angle C, then A prime is congruent to C prime. So that's how I knew that this was congruent to this. And now, here's the contradiction I'm going to get. I'm going to get that angle B is bigger than angle B, which is impossible. Alright, so I know angle B is bigger than angle A, right? That's what we started with right here. I know angle B is bigger than angle A. What is angle A congruent to?
A prime.
A prime. What's A prime congruent to?
C prime.
And how does C prime compare with B prime? It's bigger than it. How do I know that? Because R is in the exterior of this angle. R is in the exterior of this angle. So that's how I know that C prime is bigger than B prime. And how does B prime compare with B? It's congruent. So I got B prime is greater than something is greater than B prime, or B. So I got angle B is ultimately greater than angle B. Angle B is greater than angle B. But I know that
Angle B has to be equivalent.
every angle is congruent with itself. And so no angle can be larger than itself and no angle can be smaller than itself. So that gets us a contradiction. That's our contradiction symbol. And the contradiction symbol is an arrow pointing this way and an arrow pointing that way. Two arrows pointing at each other. Contradiction. Therefore, A has to be congruent to B. Because if A wasn't congruent to B, then we could get that B is larger than itself, which is impossible.
Right.
And so A has to be congruent to B.
Okay.
Good?
Yeah.
Our last definition is what it means for two lines to be perpendicular to each other. What does it mean for L and M to be perpendicular?
If their intersections are right angles.
Their intersection is right angles. So two lines, L and M, are perpendicular if their angles of intersection are right angles. And we write that as L is perpendicular to M. And that's our perpendicular symbol. Make sense? That's our last definition. That's the end of chapter 6. Now all you have is homework, and then we're past the hard part of the class. Good? All right. Enjoy your homework and enjoy your break.